So, hello. I'm going to do something slightly different than what I normally would do. Usually, I'm doing lessons in leadership, but I did recognize that I never talk about tech. So today, I'm gonna do a tech walkthrough of the architecture of a compiler that I wrote and kind of how the pieces come together from the front end of the compiler all the way to the back end abstract machine that's running the compiler instructions. So this is going to be long compared to what I usually do. It is also not at all scripted or orchestrated. I kind of have a little bit of setup, but it's going to go as it goes. Sorry. What can I tell you? We're going to talk today about a language called eval. And what eval is it's a Lisp environment of sorts. Specifically, it is a Lisp 1. Reminiscent of Scheme, influenced a little bit by Clojure as well. It is designed specifically to be hosted inside of a Go process, meaning that it is not really a standalone Lisp, although there is a read eval print loop that I will show you. And ultimately, it's mostly designed to be able to script Go. And so let's get into it. I'll show you very quickly what I mean by the Reppel, which is this. It looks like most Reppels. It's not the most feature complete Reppel in the world, but it will suffice for testing the language out. So you have your standard things like doc, and then you could get the documentation for some of the forms that are included as part of the runtime. The Chan form, for example, will create a Go channel. The way I implement channels is slightly different. They're actually implemented as lazy sequences, and the reason for that is because eval is designed to be completely immutable, with the exception of what I'm about to show you, which is the define function. So if you're familiar with Lisp, Scheme, whatever, there is the idea of doing a def or define, and def would be something like define pi as 3.14, right? And that will create a symbol in the current namespace. In this case, it's called the user namespace. And then every time I refer to that name, it will return the value that's been defined in that namespace. Now, it seems pretty simple on its face, but there's a lot that happens there, both in defining the variable and then being able to resolve the name to retrieve the value that's associated with that variable, because those associations can happen on multiple levels. There can either be a definition in the current namespace. There could also be a local variable that's been declared and assigned and bound to within the scope of the current running function. And there could also be arguments that are being passed into the function. And so the compiler has to know all of this based on the tree that it's provided to evaluate and compile. So let's talk about define. I'm going to show you very quickly define itself. This is how the define function is defined in the language. And one of the things you're going to see is that it is a macro unto itself. I'll talk about macros in another installation. This would be its name. Then there's a dot, which basically means that it's going to treat the rest of the forms provided to that Lambda / macro as a single argument, and then it can use those to iterate over the elements of the body. Now, first thing I'm going to do is I'm going to let value equal the first element of the body. The idea there is like I need to investigate what that value is. If it happens to be a list, then I'm going to treat it as the functional definition syntax of define. If you're familiar with Scheme, then you'll know what that looks like. But if it's a symbol, then I'm just going to revert to the standard minimum viable behavior of define, and that is here. And you'll notice that there's a star here. And this is basically a convention that I use. I've seen it in other places as well, that says this is sort of a basal function, and its purpose is to do something very, very close to the abstract machine. And it only does one thing, and there's no variation in how it does those things. So what we need to do from that point is we need to say, well, where is define star defined? And actually, if you want to find it, it's in another file called asm. And this is where we're starting to get into the compiler. Now, to be able to define a function in the global namespace, you would usually have to use define, but define star doesn't exist at this point. So we have to bootstrap it. And the way that we bootstrap it is we need to break it in. We need to issue assembler commands. And by the way, this assembler looks nothing like any assembler you've ever seen. If you're familiar with x86 or ARM assembler, these instructions and opcodes and directives are designed specifically to drive the abstract machine that operates at the heart of eval. So what we have here is we have an assembler block. It's going to push a constant to the stack, and I should say that the abstract machine of eval is a stack-based machine, although there are locals that can be used as registers. There are no instructions that are specific to shifting between local values yet. I'm not sure if I'll ever do it, to be honest with you, because the computational model of Lisp is actually very amenable to a stack-based machine. And so it may be that it's always like this and it doesn't need to change, but that's yet to be determined. So I'm pushing a symbol, const, declare star, onto the stack. I am then instructing the assembler to do a sub-assembly evaluation. And this assembler block is actually having a directive called make encoder. And what make encoder does from the assembler point of view is it creates a new encoder function. And an encoder function in eval is actually a Go function that's designed to accept an encoder object. And the encoder object is what you use to emit instructions and opcodes to the optimizer, and then ultimately what will become the representation that the virtual machine or abstract machine is using to run your program. I'll quickly show you what the interface for an encoder is. This is the interface, and by the way, this is Go code. Like I said, it's written to be hosted in Go, and so therefore I wrote it in Go. An encoder is simply an interface. It does embed value because an encoder needs to be value because you need to be able to pass them around inside of eval, and value is sort of the basic interface of data in eval. With it, you can create a child encoder, but more importantly, you can emit opcodes and their operand. Right now, there's only one operand as far as the instructions are concerned. And again, there may never need to be more than that. Most of the time, they don't even require an operand, like push, pop, no operand necessary. You then have a function called code, and the idea there is that everything that's been emitted up till that point will be materialized into a set of instructions as a slice of instructions, which are basically just 32-bit unsigned integers. You can get the stack size. The idea is that at any one point, the encoder is tracking how much you've pushed or popped from the stack, so you can get kind of the high watermark of the stack that you're going to need to operate the function that gets generated. And that's another thing, is that everything that gets encoded in eval will ultimately be turned into a Go function that accepts a variable number of arguments to it. And each function is a separate abstract machine unto itself. And the nice thing about that is that you don't have to worry about sort of a global machine that has to do tracking of a lot of different variables. Anyway, you have the ability to create a new label. Labels are ultimately operands, and the encoder itself is tracking them uniquely. So beyond that, you have globals. So for this encoder, what is its global namespace? Like, where is it looking up its globals from? And this is used for resolution later on. You have a set of constants, so that as you're encoding, any constants that you've referred to in the encoding will be stored in this constants set, and that becomes part of the representation of the lambda that gets compiled. Of course, you have the ability to add those constants, and you get an operand for where that constant exists within the constants values set. You then get the closure, and this is the idea here is that you get a set of cells and where they're actually coming from, because what eval will do when you instantiate a function is it will initially grab copies of all of those values from the enclosing function and then store them in the instance of the function to be passed around, so that you don't have to have these like long chains of closures that stick around forever. Like, once you've actually instantiated a closure, it is effectively severed from its parent scope. And the reason why that's possible in eval is because everything is immutable in eval, and therefore you have guarantees that you don't have to worry about a mutation in a parent scope affecting something in the child scope. It makes it very easy to compile when you're doing it like that. It's no exit analysis or anything is necessary in that case. Push params, pop params. Every function that gets created is going to take parameters, or take arguments as defined by params. This is where you would push the names of the parameters that are going to be part of the current executing scope when you've been encoding. Pop does probably what you think it would do. Resolve param, specifically, that's going to do a lookup of the current parameter scope and resolve which one it happens to be from the point of the indexed locals, because there will be copies that happen. You'll get a local count, and what I mean by local count is you can call them your ad hoc registers, but it's going to be a set of local values that you can just do whatever you want with from the compiler's point of view. And of course, it's also going to track a high watermark. You can also push and pop them as a set, and the reason why you would want to do that is every time you do like a let, you're going to create some locals, and you're going to bind those values. You may also shadow the same name from a higher part of the local stack. And so it's tracking those things for you. So it never creates too many locals, and it also will reuse local cells once the scope has been popped away, because it doesn't necessarily need to keep them around forever. Add local allows you to add a local reference. Now, the interesting thing here is that for bindings, you will definitely need a name, but ultimately, as far as the compiler is concerned, the name is completely forgotten after everything has been compiled. And then you have resolve local, that basically says you give it a name during the encoding phase, and you get the cell back where you know you can retrieve that local in the future. And then finally, there's a function called resolve scoped. And the idea there is that if you give a name to resolve scoped, it will walk the state of the current encoder to determine from a rules point of view what that name should resolve to. Because again, it could resolve to a local, it could resolve to one of the parameters of the current function, or it could resolve to something that's been defined in the global namespace of that encoder. And so this would be the thing that tells you what that cell is and where it comes from, so that you can generate the proper code for retrieving it at runtime. So that's the interface. And the assembler itself basically drives this interface, and it's a very simple assembler. So let's go back and look at some of that code. I can give you an idea of exactly what it's doing. So you're making an encoder, right? And it gets a parameter, and the parameter is name, so that argument comes in. And then what I'm doing here is I'm pushing a const of name, and you should know that an encoder is a normal function, is not an applicative function, meaning anything that you pass into that encoder is going to not be evaluated by the language. Now in Lisp, most lambdas that you create are considered applicative, meaning that anything that you're going to pass into it as an argument will be evaluated before it's passed in. That's different than a Lisp macro, because a macro is considered kind of a normal function, meaning that you have the function, things you passed in will not be evaluated. They will remain in their original form, which is whatever was read by the reader. So this just gets passed in because ultimately I want to declare a name in the current namespace. I'm duping it. And the reason for that is because after this encoder runs, it's going to want to return the name that it registered. And then I'm calling the declare instruction. And the declare instruction basically creates a public entry in the currently scoped namespace based on the name that it popped off of the stack. That's it. After I've done that evaluation, I'm calling bind. And the bind instruction basically says, pop that first value off the stack. That is the thing that I'm going to be binding. And then pop the next thing off, and that is the name I'm going to bind it to. And in this case, that's exactly what's happening here. So I'm basically doing a binding of the declare function to this encoder that I've created. Now, same thing happens with private. And the only difference between these two is that private is a private declaration in the current namespace. Anything operating inside of that namespace has access to it, but anything trying to resolve that name from outside of that namespace can't see it. That's it. That's the main difference. And it makes it easier to be able to create like private functions inside of your namespace that are like utilities that you don't want to export without having to resort to things like defining them inside of a let or something like that. So next would be define. This is your define star, and that's what I was calling before at the more abstracted version of define. And ultimately, it's very similar to the other ones. And it's going to be that I'm creating an encoder that's being assembled. It takes a name and a value, right? Because you're ultimately going to do a define and bind. And you're going to push the constant name onto the stack. You're going to duplicate it again because it follows sort of the same semantics as before. And then you're going to evaluate the value. In this case, this normal function has to evaluate that value. And what eval does is it basically generates the proper compiler code to be able to fully evaluate whatever value you passed into it. And then finally, I'm going to bind it, right? So same semantics. The idea is that value is evaluated, and then I take the name and I bind that value to the name. Now, why are there declare and define as two separate things? Well, the main reason is, like I said, I really try to push the idea of immutability in ale. And if you're creating an immutable environment, you have to be really careful about breaking values or redefining values. So ale does not allow you to redefine values, which makes it really hard at the namespace level to be able to refer to something in a circular fashion. So what I do is I allow for the name to be basically a forward declaration, either a forward public or a forward private declaration. Now, it's not necessary to do that. But it's valuable to do if you need to be able to do circular referencing at the namespace level, but not necessary. You can get by with just doing define. So the idea with define and with, let's say, declare, from a compiler point of view, is that in normal compilation circumstances, when I did that resolve scoped, if you had not declared a name up until that point, the compiler will blow up. It will not attempt to even compile something because from a scoping point of view, it doesn't see that name anywhere. And so it can't safely generate any code for the abstract machine. And so it just explodes. It says, no way, I'm not going to do this. And the way around that would be that you can create a forward declaration of something. Now the compiler knows that it's been declared. It also knows that it hasn't been defined yet. And therefore, it will generate different kind of code for resolving that name. In the normal case, if it can resolve the value from the namespace at compile time, it will completely forget the name. It will just use the value and embed the value as a constant in the compiled function, and therefore the namespace doesn't matter again. This is again the value of having a very immutable system, is that you could just forget about the namespace where those values came from. But if it's only been declared but not bound, then you do have to create a little bit kind of a different resolution code. And the idea there is that it's a late binding code. So it's a reference. The value that gets stored is going to be essentially a pointer to the namespace where it came from, and the name of the value that needs to be resolved at runtime. And it will resolve that value at runtime every single time it runs. There may be some opportunity in the future to actually do like hot code swapping, but I'm not going there right now. This is way too early days. And so not something that I'm worried about right now. I just want to get the mechanism working at this point. So there you have it. That's your declare define. And if you scroll down, you'll also see that there are some other assembled functions in eval as well. Your standard quote function is just pushing the value provided as a const, which is exactly what you would expect for quote. Your car and cutter functions are doing kind of what you would expect. You have a const being passed into a lambda, and that's another thing. You can just embed the ASM anywhere you want to emit assembler code that targets the abstract machine. And so in this case, I'm defining a lambda, and I'm basically using the define function that I've defined up here as assembler. So I bootstrapped it. And I'm calling lambda. It takes a const. I run some asm to resolve consts, and that's doing that scoped resolution. So it's saying, where's that const name coming from? Happens to be coming from the arguments to that function. And then after I've resolved it, I'm going to call the car instruction, which is one of the built-in instructions in eval. And same thing for cutter, right? You're creating car and cutter so that you can iterate over sequences and lists. Same deal with arrays, which is basically throwing an exception. In this case, it calls the panic instruction, and it does exactly what you think it might do if you're a Go programmer. And then finally, I have the if function, which is also defined. One of the nice things about the way that the eval assembler works is it sort of follows the same syntax as eval functions, meaning that if you're creating an encoder, you can actually do variable number of arguments. So in this case, you have all three, predicate, consequent, and alternative, are being provided to the encoder, and it will generate different code than if you only provided a predicate and a consequent. So if you only provide a predicate and consequent, the alternative is going to just be nil that gets pushed onto the stack, because if has to push something on the stack, it's either going to be the consequent or alternative, or in the case of not having an alternative, it has to be nil. That's essentially how it works. So when you see this, it all starts to sort of come together. Is that I've been slowly trying to get as much of the eval code into eval as possible, and with the introduction of this assembler, it is sort of speeding things up to allow for that to happen. So less and less of the runtime code will be written in Go. It won't ever be the case that there is no Go anymore, because the whole point of the design is that it has to be embedded into Go processes. But I wanted to be able to exercise the abstract machine as much as possible by being able to write the language kind of in itself. Now, one of the things you might not be familiar with is this syntax. This is syntax quoting. It's a scheme thing. It helps you to create hygienic macros. These are the escaping abilities for it, but that's a topic where you can kind of research that on your own. eval supports this kind of macro. Let's go into the basics. So these are some of the basic functions in eval. These are your encoders, by the way. So you can, like I said, you can write an encoder in the ASM, or you can write an encoder in Go. And so eval, your standard eval function, is actually an encoder, and that'll take an encoder, and it'll take a set of arguments that are data values, because it's the standard currency of eval. Now, in this case, it's going to do an assertion on the number of arguments that are provided to it, and because it's a special, it's not compiled, and therefore it has to do its own assertions. And in this case, this function needs to take one argument. and one argument only. And now it's gonna generate some value code in using the encoder, right? And so specifically, this is calling generate.value, meaning it takes that argument, the first argument, and tries to compile it. And I'll show you briefly what that is. It is the ugly, dreaded switch statement. It's going to take that value, and the first thing it's going to do is it's going to do a macro expand, because that's how the things get done in Lisp, is that you read something in, you can't compile it until you've actually called the macro capabilities, and I won't talk about macros today. And once it's been expanded, you're going to take the type, and I'm going to do type switch, and then based on that type, you're going to have to generate different code. So if it's a sequence, I'm going to generate different code than if it were like a pair or a symbol or a literal. Sequences can be kind of anything in ale. Ultimately, you've got your list, you have your objects, vectors, and so on, as well as lazy sequences. If it's a list, that's special, obviously, because in Lisp, a list is how you invoke functions, and it will look for that pattern to compile a function invocation. And then you have your literals. So if it's a keyword, a number, a boolean, or a function that's already been compiled, it will treat that as a literal and then push it as a constant onto the stack. Or in the case of some numbers and booleans, it might generate a single instruction to represent that encoding. And finally, if it can't figure out what to do about it, it means that you passed in a value that is completely incapable of being encoded by the compiler, which in this case is a programmer error, because it means I missed something and that the programmer couldn't possibly, not the programmer, the user couldn't possibly have done that themselves. It was all on me. And so you'll see those occasionally in the ale code, because the idea there is that I want to track coverage, and I want to make sure that this stuff is never getting called, pretty much. So it will remain. Anyway, going back, I'm going to just take a quick look at the ASM code. And so this is the ASM encoder. At the higher level, ASM is also a special encoder function. So it takes an encoder and a bunch of variable arguments. But ultimately, it takes those arguments and it calls this function, whether or not it's going to generate an encoder or if it's going to be inlined. And so I'm doing a standard iteration over a sequence in ale. That's done through the split function on sequence. And basically what split does is it says, give me the first, the rest, and tell me if actually this split was successful. Splits are only unsuccessful on empty lists. So if you have a list with even a single element, splits will always be successful. And this helps you determine that you've reached the end of that list. So yeah, here we go. We're in the encoder. And the way that the encoder works for the assembler is that you have only two kinds of symbols that will trigger anything. Not symbols, values that will trigger anything in the assembler. It's pretty simple, as assemblers should be. So a keyword, which is an ale value that has a colon in front of it, is a label. It's similar to how you would do a label in assembler, but it reverses where the colon comes, because keywords have colons in the beginning, whereas a label in normal assemblers, the colon comes at the end. How you refer to a label in jumps is also going to have that colon at the beginning, because it's a keyword. And so there's that. And when it sees a keyword, it is literally going to emit a label and get the label index based on the keyword name that you provided to it, which is pretty straightforward. And then there's your local symbols. So your local symbols are just a name that's an unqualified name. So it doesn't refer to any of the named namespaces of the current environment. It's going to get the name of that symbol as it's essentially a string. And then it's going to do a lookup into a table of possible calls. And now this table of possible calls, it's generated from a lot of different sources. So one will be the directives that I've sort of explicitly defined, like make encoder and local and const and eval. But it's also populated by an enumeration over the instructions that are actually defined as part of the abstract machine in ale. And so it doesn't matter because the form it takes is always the same. It's some encoder function, and there's a number of arguments that encoder function takes, and it's fixed number of arguments. And you can see that kind of here where I'm basically doing a take on whatever remains of the current sequence of the number of arguments that I need. And if that's successful, then I can call the function and then set the rest of the iteration to R. Pretty much. And then it explodes if it can't figure that stuff out. Like I said, it's a really, really simple assembler. And the thing about the calls, especially when it comes to the instructions, I should probably say is that there's, where is it? Here we go. So get instruction calls. These are your instructions for the abstract machine. I've wrote this so fast I forgot what I named the methods. So what it's doing is it's gonna create a call map, and call map is just a mapping of name to call. And it's going to be based on the size of something called effects, which is in the ISA package of the compiler. And the way that works is that it's going to go in and then it's going to get some information about the opcode that's defined. And then it's going to convert the name of that opcode into snake case, because normally they're in camel case because they have to be in Go. The snake case is the way that you would invoke that instruction in the assembler. But important would be what ISA effect looks like. So I'm going to jump into it right now. Any single effect kind of looks like this. You get an operand and it's going to act on something. And what it will act on is nothing potentially, but sometimes it'll act on arguments, constants, generally take an integer to do things, or push a constant integer onto the stack, for example. It might act on labels, it might act on locals, it might act on the stack, and on local values as well. Other values, I'm sorry, coming from the closure. So here are the actual effects and how they're defined. And what you'll notice is that these are your opcodes for the abstract machine. Your standard add, right? It's going to pop two things off the stack and it's going to push the result onto the stack. It's not doing anything special, so the default, of course, of act on for the operand would be nothing. And so I didn't have to actually put that in here. Arg is going to, which is very pirate-like, is going to push a value onto the stack, and its operand is going to be using the arguments that are passed into the Lambda that's generated by the compiler. Arglang is just going to push the number of arguments onto the stack that were provided to that function, and so on. But going down here, you'll see that there's an instruction called declare, and we were using that before. And declare will basically just pop a local symbol off of the stack and create an unbound namespace entry for that local symbol. And bind, when we come back here, there's your bind. And what that's doing is it's basically it's popping a value off, popping the name off, and then binding that value to that name in the current namespace. That's it. I mean, it's pretty straightforward. And if you want to look, the actual code for these is pretty much right here, and it's relatively straightforward, right? You have because I'm popping something off the stack, I'm incrementing the stack pointer. The stack in L's machine grows backwards, and so I'm incrementing it, making go forward. I'm then basically retrieving the Lambda from the current instance of the closure, and I'm referring to its global space, and then I'm saying, hey, I want to declare this value from the stack in the global namespace that is available to this encoder. That's it. Same thing for private, but it's called private. And then bind, it's pulling two things off the stack, so you're going to see the stack pointer incremented twice. Could be that I convert that into one function, but I'd want to make sure that we understand the semantics of what's happening in the machine rather than trying to optimize the hell out of it right now. But it's going to actually do what you saw it do here, which is declare, because if you're going to bind something, it doesn't have to be pre-declared in order to bind it. And I didn't want to have to emit two sets of instructions just for the initial declaration and subsequent bind. And so binding allows for something to be declared if it hasn't been already declared. And it'll try to do it as a public declaration, but if you've already forward declared it as a private, then it remains private. This is just basically what you should know about what the compiler does. It won't make it public after that. Yeah, that's it. And then you've got the ability to resolve from the namespace. So there you have it. It's just a call to must resolve value. It will explode if it can't resolve that value. And then, for example, for finding things like locals, you're going to have locals that are defined. There's where your closure is defined. These are all sort of the registers of your abstract machine. You've got your data, which is pretty much the entirety of the current stack and your locals combined. And then I take sub-slices of those to do bookkeeping. And the good thing about slices in Go is that you can't actually read out of bounds, which is great, right? So you can never do like stack smashing or anything like that in this abstract machine. It'll explode rather quickly if you mess things up. Then there's the stack pointer. There's the program counter. The program counter will start off at 0 and then just increment until you hit a jump. And your jumps are going to either be absolute jumps or conditional jumps, and they're pretty straightforward. One thing while we're here is that Scheme, at least, I'm not sure about Common Lisp, I could be wrong, but Scheme at least requires that you support tail calls. And so Ale does do that. There's a lot that goes into it from the point of view of the compiler. So the optimizer, once you've given it a bunch of instructions, you don't have to tell it to do a tail call, which is great, right? You don't have to set up any instructions that say, hey, do a tail call. You actually just do a normal call, and then the optimizer will look at the patterns of how you're calling things. It'll see that you did a function call and an immediate return from that function. And because of that, no matter where that pattern happens to be in the current Lambda, it will encode a tail call. And the tail call is, again, pretty straightforward, right? You're going to get, you need arguments that are provided to that call, which it's actually doing right here. And then you're going to call the function. And the way you get the function would be that you are taking the function that was pushed onto the stack, because that's the next thing that comes out of the stack. And then after that would be your arguments. No, I'm sorry. Yeah, after that. I've sort of done things in reverse order here. And then I'm going to do a check, right? I'm going to check, is this a closure, meaning is it the internal representation of a compiled Ale function, like one of these abstract machines? And if it is, yay, because I can actually perform the tail call. But if it isn't, so for example, if it's a Go function, there's no way to actually encode a tail call for the Go function. And so what I have to do is I have to just invoke it normally by passing the arguments into it, pretty much. And one thing, this is just a gotcha for Go coders. If you have, like, for example, a stack structure where you're going to take values off of it, and then you're going to pass those values into a call with the spread operator like this, you got to be really careful, because that is a slice of the original stack. And when that stack changes, that function, those arguments will change with it, because they're both mutable. And so what I do to work around that, even though it's going to be slower, is I make an actual copy of the arguments, and then I pass that into the call to the function, because it's much safer to do. Now, of course, there's a cost to that, but the cost is worth not having things explode after the fact, especially when you have concurrency going on in the code that you're producing. If it were a normal single thread thing where it's a stack and you're popping out of it, it probably wouldn't matter at all, because the stack remains in place. But if you're going to call like a Go routine and run it in a separate thread, now it's operating in a long-term fashion independent of that initial stack, and the stack will change after the fact. So you have to be careful here. Now, the next thing that I'm going to do is kind of an interesting thing. If The value closure that I have already determined it is a closure happens to be exactly the same as the current receiver. And by the way, when I say current receiver, this machine will change the Go receiver. You can see it right here. But if it's the same, I'm going to just go to init state. And what that means is that I'm going to go back and I'm going to reset the program counter and the stack pointer. That's it. Literally, that's it. And you know, the arguments are already provided because I've also overrode the arguments that were part of the closure itself. So yeah, there you have it. And if it's not, so if then what I'm going to do is I am going to override the current receiver, which you can do in Go because it's just a value at the end of the day. And then I'm going to check if I have to resize the data segment for some reason, because not all functions will have the same stack size. Like I said, there's a high watermark on the stack size, and not all functions will have the same high watermark for locals. And so if any of that changes, I do have to reset the data available to the function. But generally speaking, that's not such a big deal. It will happen occasionally, but most of the algorithmic patterns that you tend to see in Scheme and EL as well is that it's usually going to be self-recursion. And if it's self-recursion, that's great because you don't have to end up doing kind of the shenanigans right here. But when that's all done, then you just go to the init state, resets the stack pointer and the program counter, and then it just resumes without having to push any more stack frames on the Go stack, which is fantastic from an algorithmic point of view. All right, so now you probably understand how typing define pi 3.14 ends up in something where I can say pi and it resolves. And in this case, it's a global namespace, but it could also, like I said, be a local or an argument. I hope that was informative, and I'll do this again if you like it. Otherwise, I'll just get back to doing the leadership complaining. See you.